everyone, in this section, let us introduce the Cantor Schröder-Bernstein Theorem, which offers a very nice alternative approach of showing that two sets have the same cardinality. First, let us look at the following definition, where given two sets A and B, we say that the cardinality of A is less than or equal to the cardinality of B if there is an injection from A to B. For instance, if A is a set, then the only function from the empty set to A is the trivial function, which is an injection vacuously. As a result, we can say the cardinality of the empty set is less than or equal to the cardinality of an arbitrary set A. Now, if A is a set, S is a subset of A. We have already seen that the natural inclusion map from S to A will also be an injection, indicating that if S is a subset of A, then the cardinality of S is always less than or equal to the cardinality of A. As another example, let us consider two sets A and B, where B is not empty. Recall that we can fix an element, say lowercase b, in the set B, and from there we can construct an injection from the set A into the product set A cross B, sending each element x in A to the ordered tuple xb, where B is the fixed element in the set B. This function embeds set A into a slice of the product set, which can be identified with a copy of A. Because of its injectivity, the cardinality of A is less than or equal to the cardinality of A cross B. Be careful. Here, the assumption that B is non-empty cannot be dropped. Otherwise, the conclusion is no longer true. Finally, imagine that we are given three sets, namely A, B, and C, where the cardinality of A is less than or equal to the cardinality of B, while the cardinality of B is less than or equal to that of C. In other words, there is an injection F from A to B and an injection G from B to C. Now, their composition will be an injection from A to C, indicating that the cardinality of A is less than or equal to the cardinality of C. This transitivity might be very useful in our later discussion. Now we are ready to claim the Cantor Schröder-Bernstein Theorem, which states that given two sets A and B, if there is an injection from A to B and an injection from B to A, then there exists a bijection from A to B. In terms of cardinality, this can be stated as if the cardinality of A is less than or equal to the cardinality of B, and the cardinality of B is less than or equal to the cardinality of A, then A and B are of the same cardinality. This theorem can be very convenient in proving that two sets have the same cardinality. After all, for arbitrary sets A and B, it might not always be evident how to construct a bijection from A to B. Recall that a bijection is a function that is both injective and surjective. In other words, our construction of this function must satisfy two conditions, which can be very demanding and complicated. Now, the Cantor Schröder-Bernstein theorem offers us a trade-off between the quantity and the quality. Instead of having a finished product, that is, a bijection between A and B, a pair of semi-finished products might also make things work. We will see, in some scenarios, the construction of two injections can be way easier than looking for a single bijection. To illustrate how it works, let us revisit some of the examples we have studied in the previous section. There we have proved that the given sets have the same cardinality through construction of a bijection. Now, let us reprove the same conclusion by applying the CSB theorem, that is, by construction of a pair of injections. First, let us reprove that the product set n cross n and n itself have the same cardinality. Recall that previously, this is done with the help of the Cantor pairing function, whose construction, although natural and elegant, might not be that trivial. This time, let us define the function f from n cross n to n, where a given ordered pair of naturals m and n is sent to 2 to the power of m multiplying 3 to the power of n. To see this function is indeed injective, let us assume that two ordered pairs of naturals, namely m1 n1 and m2 n2, are mapped to the same natural number. In other words, 2 to the power of m1 multiplying 3 to the power of n1 is equal to 2 to the power of m2 multiplying 3 to the power of n2. Now, due to the uniqueness of prime decomposition, as is guaranteed by the fundamental theorem of arithmetic, we see that m1 is equal to m2 and n1 is equal to n2. In other words, these two ordered pairs are identical, implying the injectivity of f. For the other direction, let us consider the function g from n to the product set n cross n, sending each natural number n to the ordered pair n0. This function is clearly an injection, as we have explained earlier in this section. Now that we have obtained two injections in both directions, a direct application of the CSB theorem shows that these two sets have the same cardinality. As a second example, let us reprove that the left open right closed interval 0,1 and the open interval 0,1 have the same cardinality by using the CSB theorem. To start with, let us consider the affine function from the left open right closed interval to the open interval, sending each x to x over 2. As an affine function, it is clearly 1-to-1. Moreover, the image of f will be the left open right closed interval 0, 1/2, which is a subset of the open interval 0,1. As a result, the function f thus constructed is indeed an injection from left open right closed interval 0,1 into the open interval 0,1. Notice that the open interval 0,1 is indeed a proper subset of the left open right closed interval 0,1. Thus, the natural inclusion map will be an easy candidate of injection for the other direction. Again, since we have constructed an injection for each direction, the CSB theorem permits us to conclude that these two intervals are of the same cardinality. As you can see, with the help of this powerful theorem, our proof can be done by merely using functions as simple as the affine ones. Compared to our previous approach developed in last section, where we have to cleverly observe a partition for each set and then construct a piecewise bijection between components of partitions, the approach here, thanks to the CSB theorem, seems to be considerably easier.